session is covered by Dr. Y. Rajashekhar. Dr. Y. Rajashekhar received his bachelor's degree in mechanical engineering from Jawaharlal Nehru Technological University in 2002, master's and PhD degree in energy systems from the same institute during 2005 and 2017 respectively. He has nearly 15 years of working experience, which include 10.5 years in teaching, 4.5 years in research. He also worked as lecturer at Institute of Science and Technology, JNTU, Hyderabad, and research scientist at SSN Research Center, Chennai. Dr. Y. Rajashekhar is currently working as an associate professor in Department of Thermal and Energy Engineering, associated with the School of Mechanical Engineering, Vellore Institute of Technology, Vellore campus. To his research interest, he has published research articles on high impact factor Thomson Reuters journals like Environmental Science and Pollution Research, Sustainable Water Resource Management, International Journal of Renewable Energy Research, ASME Solar Energy Engineering, etc. He has nearly 50 publications, which include 20 Scopus indexed international journals, 25 international conferences, and 5 national conferences. He is currently guiding PhD program in the area of sustainable energy using renewable sources of energy. He is serving as a reviewer for many international peer-reviewed scopuses and Thomson Reuters indexed journals. He is associated editor of Energy and Thermofluid Engineering Journal and editorial board member for the Science Journal of Energy Engineering. He also bears life membership in Indian Society of Heat and Mass Transfer, Solar Energy Society of India, etc. His area of interest include thermodynamic evaluation of renewable energy systems, developing low-cost sustainable solutions for domestic and process engineering applications using renewable energy sources. Our heartiest welcome to you, sir.
Yeah, thank you for the nice introduction. So I'm really honored to be a part of this FDP session. I will share my screen. Is the PPT visible? Hello. Is the presentation visible to all?
Yes, sir, it is visible.
Yeah, thank you. So, good morning, one and all. So, I'm really honored to be a part of this AICTE Training and Learning Academy FDP program on solar energy technologies and application. So, organized by Jyoti Engineering College. So, I really thank the organizing team of this 5-day FDP for choosing me as the resource person. So today I will be covering a topic on solar thermal collectors. So basically this solar thermal collectors utilization is very vast, but I will be concentrating on performance enhancement with passive techniques, especially this solar flat plate collectors. So this will be my presentation outline. So I think most of it has been covered by Professor Reddy sir in the morning during his first session. So the energy scenario. So the amount of energy received on Earth, then the solar thermal energy conversion possibilities. Then I will be covering on parametric analysis of flat plate collector, a numerical approach, and some basics of nanofluids. And I will be discussing on two modes of heat transfer, that is natural convection heat transfer as well as forced convection heat transfer, and how we can utilize these nanofluids for enhancing the flat plate collector efficiency. And finally, the summary of this. So before starting, I want to sincerely thank my gurus and the collaborators in different parts of the world for presenting this work. So the work I am presenting is some part done by myself and some with collaboration with different research groups in Malaysia and Europe. So coming to this introduction of energy resources, as Professor Reddy has pointed out, so the utilization of these conventional sources has been rising, but now all federal governments has realized that so the conventional utilization has to be stopped due to a rise in the greenhouse gas emissions. So as you can see here in this graph, so the purple one refers to the usage pattern for different years. So this has been for a century from 1925 to 2125. So you can see that after 2000, there will be a decline in the conventional usage because of the growing importance of this alternate energy sources like renewable energy sources. And obviously the utilization of natural gas and other gas liquids will also be reduced in coming years as the global warming potential of the Earth is going to be increased. So coming to the world energy renewable sources, so this is a pie chart showing the availability of different energy sources. So almost most 50% of the resources are covered by biomass, and there are new biomasses coming, so which accounts for around 10%. So geothermal is 2.3, hydro is about 30%. And your tidal, wind, and solar energy comes in the other part of this availability. So coming to the consumption pattern, so this is the global consumption pattern. So
Excuse me, sir. All participants are required to mute the video. Sir, you can also mute the video because the bandwidth problem issues is there for many persons. So if it is only PPT, then the voice will be very clear. Yeah,
whether my voice is not clear?
Yeah, some disturbance a little bit is there, sir. So if we mute our videos, then it will be clear, I think so. Also, few participants' video is on, so participants are also requested to please switch off their video.
Now is it fine?
Yes, sir.
Yeah, okay. So coming to the world energy consumption pattern, so more than 50% of the energy is produced from conventional fuels. So here you can see around 32.6% is from oil, 22.2% is from coal, and 21.1 is from natural gas. Okay, so more than around 75% is from conventional. So around 5% by nuclear, and the renewable covers around 18.4%, which includes hydro, traditional biomass, as well as solar thermal and solar PV. So the same usage pattern is followed in our nation also. There is more than 60 to 70% is coming from conventional power generation. So that's why since last decade, so Government of India is trying to reduce the coal consumption by encouraging this renewable energy power generation through solar PV as well as biomass power plants, and we want to save the carbon emissions released from the different usage of conventional energy sources. So I want to specifically stress on the importance of solar energy in the global as well as the national context. So yes.
Sir, can you please hide that remark on the bottom of the screen?
This one.
Yes.
Yeah. Okay. Yeah. Yeah.
Thank you, sir.
Yeah, fine. So this statistics has been taken from IRENA. This is the latest statistics published by them. So to look at the installed capacity, so this is for last decade from 2010 to 2019. So the trend of installation is going in an exponential way. So where the orange ones refers to solar thermal and yellow ones refers to solar photovoltaic. So most of the power generation is happening from solar photovoltaic rather than from solar thermal. So I think what might be the reason you might have got from Professor Reddy's words. So there is a lot of scope for improvement in this commercialization of solar thermal power plants. So there are some few drawbacks which I will state it in rest of the slides. So majority of these installations, that means majority of the power is generated from solar photovoltaics. So some of the challenges which I could find is the technology readiness. So the solar thermal. So there should be some economic way of power production. So currently, only a few companies are producing this solar thermal based collectors as well as the related components. Okay, so in India, there are, we can say, count on fingers how many companies are there. So the basic reason is so the technology readiness. So people are yet to accept this solar thermal power production. So one of the reasons can be the cost. So cost of the technology. So since there are few young researchers and faculty, so we can concentrate on developing new materials for this solar thermal technology, so that the cost can be reduced. So the next aspect is the grid integration. So I think you must have noted in newspapers that so 100% electricity is the main motto of the government of India, so that the power can be reached to nook and corner of the country. So in that aspect, the grid integration aspect of this conventional to the solar thermal is somewhat not proper. Okay, so the grid integration issues are there. Then there is reliability in power generation you cannot expect in solar thermal or solar photovoltaic. Why? Because they change with respect to time. So as the day progresses, the solar intensity will increase till noon, and again the same pattern will be there from noon to evening. So unlike your conventional power plants, the reliability of power generation we cannot expect. So that is one of the challenge here. Then coming to the national installed capacity. This is for India. So in 2010, the installation has started, and by 2019 it has really picked up because of the various government policies. So here you can see that solar photovoltaics in India also are contributing more for power generation rather than solar thermal. So on a global context, if you compare, India adds only up to 6% of the global total installed capacity during 2019. And there is still a lot of scope for solar thermal installations to get the commercial output. So in India, if you look, some of the challenges is, as I said, so the amount of radiation falling from one location to other location will change. Accordingly, the physics of the system will also change. So we are yet to understand the physics of the system in complete to understand the generation capacities as well as the capabilities. So here also there is a lot of scope for us to explore. So how we can exactly estimate this energy generation related to different locations of India. So you know that from Kanyakumari to Kashmir, there is a lot of latitude variation. So based on latitudes, the energy insulation will change. So how does this collectors will behave for different latitudes? That has to be understood appropriately. I think that study is yet to start in India. So once it gets a commercial base, so then people will definitely transfer from coal-based installations to solar thermal. So one of the advantages here for this solar-based energy generation is that you can build a standalone system. That means you can generate the power and you can utilize the power there itself, unlike conventional grid where you generate power somewhere and you utilize the power somewhere. So during this transmission and distribution, so there will be a lot of losses. So to some extent, you can reduce it with this standalone solar power generation. So yeah, coming to this global electricity generation trends. So there is a consistent growth in contribution of electricity from solar thermal power stations around the world. And some of the challenges here are, so as Professor Reddy also pointed out, so energy storage is the biggest challenge. So along with generation, so energy storage also becomes a primary importance. So there are no commercial energy storage technology which can be adopted appropriately for off sunshine hours. So there is a lot of scope to work on this energy storage for getting cost-effective solutions for energy storage. And similarly, infrastructure components, design and development for transmission and distribution are also yet to develop. Why? Because the components that you use for conventional grid is different, and the components you use for renewable-based energy generation is somewhat different. So yet there is yet to have a balance between this infrastructure requirement as well as the component design and development. Similarly, power quality issues can be raised, and there is a financial and economic barrier. So as I said, these solar-based installations are initial investment is somewhat costly. So there are yet to identify the economic barriers. So how to overcome these? And the Government of India and other federal governments around the world, they are encouraging this renewable to some extent by providing some subsidies. But people are not yet ready to adopt those technologies. So yeah, coming to this national electricity generation trends. So during the past 5 years, the growth rate is exponential. So it adds to around 4% of the global during the 2019. So you can see from 2017 to 18, so there is an exponential growth in India. So some of the challenges here are social and cultural barriers, effective grid connectivity and integration to conventional grid. And the companies involved in power generation are slowly picking up, including our state-run organizations like NTPC, BHEL. So NTPC and all, instead of building coal-based generation, so they are now concentrating on building solar thermal or solar PV-based installations. So including BHEL, so it is Bharat Heavy Electrical Limited. So they are now concentrating on the infrastructure that has to be built for the next generation renewable energy-based power generation. Then there is a lack in technology transfer from global industrial giants. So as I said, only a few companies around the world, they are making these renewable-based companies. So if the technology transfer takes place between the companies, so definitely there is a large scope for installing solar-based generation systems. Then another challenge is that availability of technical manpower. So usually you need to have trained manpower to operate these. Why? Because till now, whatever the conventional based power generation is there. So for that, the training programs have been organized. But for renewable based power generation, so you need some more uh, uh, critical training where the plant can be operated without any hazards. So coming to this is one of the important aspect here. So the global job market for renewable-based power generation. So from 2012 to 18. So this is also the data published by IRENA. So from 2012 to 18, you can see there is not much exponential growth. So there is a slow growth. So once these technologies are properly adopted, definitely I think there will be a large scope for the job market. So this job market for different energy sources has been listed here. So one is the hydro, wind, solar, biomass, and other resources. So coming to only solar, so you can see that the job market for PV, solar PV is more compared to solar thermal. So there are some ups and downs in this solar thermal job market because of the company's requirement. But however, the solar PV is constantly rising. And coming to the Indian scenario, so there are India is able to give jobs for about 18.7 thousand graduates. So among that, solar is very less. So as I said, so if these solar technologies have been appropriately developed for commercialization, so probably this bar, that is solar heating, cooling, and, hello. So this will also increase, and you can see that this concentrating solar power, it is zero. Okay, so in India there is no technical companies which are commercializing this solar concentrated solar power. So if the concentrated solar power has been given importance, so this bar would have been in the positive direction. Yeah, coming to this annual growth rate for the last 3 years. So you can see that solar PV in 2018 it was highest, and maybe during 2020 it has got down due to this current pandemic. So yeah, so wind is constant. So there are installations happening continuously, and bioenergy is also reduced into 2020 because of various reasons. And hydro also, since there are limited water resources in India, so slowly the market is getting already whatever the potential is there, we are using it effectively. So these are the, I think these statistics we can get it from any. So one major thing what I want to stress here is that so India is capable of producing 356,100 megawatts of energy from renewables. Sorry, in total, and from renewables it is around 123,040 megawatts. So still this gap between the conventional and renewables can be reduced by increasing the solar thermal installations. Yeah, so by this is the statistics by different sectors, state, government, central, as well as private. So private are leading. As I said, they are investing more compared to other government agencies. So as I said, NTPC, BHL, they are also leaning towards this renewable sources. So probably these numbers may change in future. Yeah, coming to this utilization of energy received on it by different ways. So this is in gigawatts. So all the numbers are in gigawatts. So we are receiving about 173 million gigawatts of energy from the sun, and out of which almost 1/3 is going back as reflective radiation in the form of shortwave radiation. So which is reflected by clouds and whatever the water is there in the atmosphere and the ice. So most of them, 1/3 is reflected in the atmospheric itself, and rest of the 2/3, so the energy is transferring into many forms. And yeah, so actually, whatever the energy we are receiving, so the same energy has to be radiated back, so that the Earth's atmosphere, Earth's surface temperature is maintained constant. So if the energy that we are receiving is not equal to energy whatever is radiated, so obviously there will be a change in the Earth's surface temperature, which is what is happening now. So because of this greenhouse gas emissions and all, so this output long wave radiation, whatever is there. So whenever this CO2 emissions increase, so this CO2 gases will absorb this long wave radiation, and again it will reflect back to Earth's surface. Okay, so the more the amount of CO2 concentration, so the reflection will be more. And also during night, so whenever there is clouds are there, so cloud will also will reflect some of this long wave radiation. Okay, so that's why clear night skies will have cold weather compared to cloudy temperature. Okay, so yeah, and what is the amount of energy that is received outside this Earth atmosphere is almost constant. So which is about 1367 watt per meter square, and this short wave radiation is absorbed by the ozone and only visible to some part of infra. The radiation is only receiving the Earth's surface, which is transferred to many forms, as you can see here, tides, evaporation of water, and this waves and wind energy. So like that it will be. So as I said, so definitely there is need to reduce the carbon emissions so that this energy balance is maintained. So if more and more of CO2 emissions are there, so the more the reflection of long wave radiation, and it will cause the greenhouse effect. So coming to this solar thermal energy conversion, so there are many conversion appliances are there. So I will be concentrating only on this flat plate collector. So this is a very useful application for water heating. So this schematic diagrams explains the operating principle. So where this is a collector, solar collector, so which will absorb the energy from the sun, and whatever the cold fluid that is flowing through this collector, it will become hot, and you will be getting hot water. So here, one thing you have to understand is that so the amount of energy absorbed depends on the area and what type of fluid you are sending it into the collector. So basically, this collector will convert the incoming solar radiation to thermal form. So another advantage here is that it can use both beam and diffuse solar radiation. And this is a stationary collector. It does not require central acting, just like your concentrated systems. The construction of this collector is very simple. It is cost effective, and I think in the morning session, some of the few people have asked, it is very expensive. So it is not expensive, and all state governments are giving enough subsidies to purchase these renewable devices, especially in Karnataka and all, if you see. So they are providing almost 50% of subsidy. So if you are ready to purchase this, so they are ready to provide 50% of the cost for installation. And maintenance also, it is very low. So unlike your concentrated collectors, if there is dust deposition on the mirrors, so you have to clean it occasionally so that the reflectivity is maintained. So this one, so usually whenever dust is there, so usually the wind that is blowing over this collector will take away that dust. Okay, so coming to maintenance, only you have to clean this top surface for 15 days once. Yeah, coming to this different components in this collector, so you have this collector box made of a metal, and you have this light blue colors are the risers, which would be around 1 inch diameter, And you have this bottom header and top header. So in between these headers, so there will be riser tubes. Okay. So this bottom header is the one wherein you get cold water, and whenever the sun's rays fall, so you have an absorber plate. So this absorber plate absorbs this solar energy, and it will be coated black in color. So you know that black surfaces absorb more heat. So the heat that is absorbed by the collector is given to this riser tubes. So slowly the water gets heated up, and because of this thermosiphon effect, so the water comes in to the top header, and then the hot water you can get at this outlet. Okay, so this is connected to a storage tank, and you can see there is a glass over this whole system. So the advantage of this glass is that so it will transmit short wave radiation, and it restricts the long wave. So as I said, the incoming radiation, whatever you have, most part of it is visible, and some part is short wave, and rest of it is long wave radiation. So this short wave and visible radiation is transmitted through this glass surface. So at the other end of this glass surface, so it will become long wave. So the energy, whatever is coming in, so it will retain within this space. Okay, so the water will continuously, so as long as the solar radiation is available, so this water gets continuously heated up. So the temperature of water rise depends on the intensity of radiation. Okay, and to protect water seepage and all, so you can see some gaskets are provided. So this glass cover is otherwise called glazing, and usually 4 mm low iron glass is preferred. So why low iron glass is that it will have more transmission characteristics compared to glass with iron. So the transmission of this glass should be around more than 90%. So then only the radiation transmission properties will be good. And these absorber plates are usually made of copper. So because you know that copper is a good conductor of heat. And at the bottom, some insulation is provided on 3 sides except on the top, so that heat losses are avoided. And whatever now I have explained is about the natural circulation. So that means through gravity, the water will pass through this collector. Another mode of operation is you can have a pump at this bottom header, so that water flows in a fast way. And you have different absorber configuration also. So I think Professor Reddy has told transparent insulation. So this is how the transparent insulation will be there. So there will be a gap between the glass and the absorber plate. So in between the glass and absorber, you can see some transparent insulation provided, so that heat losses are reduced. So basically, you know that so why this transparent insulation is provided is that so you have a temperature difference between this glass and absorber. Okay, so glass, since it is exposed to outside environment, so it will be at a lower temperature. And since this absorber is continuously getting heat, so the absorber plate will be at a higher temperature. Okay, so you know that heat transfers from higher temperature to lower temperature. So because of this, so there will be a re-radiation happening from this absorber plate to the glass cover. Okay, so to avoid that, so transparent insulation is provided, so that heat losses are reduced and heat transfer is improved. So you can say that this providing the transparent insulation over the absorber is also one type of passive enhancement. And this is standard flat plate collector. So insulation is provided on 3 sides, and you have a roll bond absorber. That means this absorber plate acts as a fin. Okay, so when the fluid passes through this tube. So the absorber plate gives heat to the fluid, and the fluid gets heated up. And you have another configuration like a vacuum flat plate collector. So this is just like pins, providing pins, and making the whole chamber completely vacuum. And you know that the heat transfer in vacuum is somewhat less. So instead of providing insulation on three sides, so you have provided vacuum here. And you have collector with limited convection. That means providing the collector with two glass covers. Okay, so people have also tested what happens if two of one, if two glass covers are provided and they have analyzed. And they have identified that so the heat losses are reduced. Similar to air, similar to water, we can have air also pass through this collector for getting hot air for drying systems. As I told, can use a pump in the circulating fluid so that it acts as a forced convection. So what is the advantage with this forced convection is that so in natural convection, so the number of cycles the water passes through this collector is limited. So it all depends on how the radiation varies. So actually, so this is a closed circuit. So either it may be for circulation or natural convection. So the whole fluid circuit is closed loop. So whenever this cold water gets heated up, that means some mass of water has been pushed from this collector. The same amount of mass will be coming and occupying this fluid inside the collector. So that's how the natural convection works. However, in this forced circulation mode, so the pump forces the fluid to pass through this collector. So the advantage here is that so the number of times the fluid will come in contact with this collector will be more. So you can ask one thing. So whether you will be getting higher temperature at the outlet. So definitely not. Why? Because so the time that is retained by the water in the collector is less in this forced circulation. That means the fluid passes very fast through this collector tube, so that the time that is available for heat absorption is somewhat less. So that's why the collector outlet temperature is less in forced circulation compared to natural convection. However, so if you want to heat more amount of water within less time, so definitely this forced circulation will be there. So on what factors this efficiency depend? So one of the factors is the incident solar radiation. So as I said, the input that you are giving to the collector will play an important role. So you know that efficiency is output by input. So as your input varies, so your output will also vary. So to find out this efficiency, so you need to know what is the radiation that is falling over the collector. So you can do that with the help of meteorological parameters like ambient air and what is the wind velocity, what is the average temperature over that location, what is the rainfall and other aspects. So if you have a weather station, so you can take the data of a few years and you can come up with the radiation possible over that location. Based on that, you can find out what is the efficiency. So the data, whatever you collect, you can develop a regression equation based on the ambient temperature, wind velocities, rainfall, and other things, and you can easily get what is the radiation possible over that location. So the difference between this incident radiation and the useful energy is the amount of energy lost to the atmosphere. Okay. So first one is you need to find out what is the incident radiation, and the second one is the amount of energy used by the collector. That means amount of energy used is the temperature difference between inlet to outlet. Okay, so the temperature difference between inlet and outlet depends on the incident radiation. Okay, if this incident radiation is less, so the outlet temperature will be less, and the delta T, whatever you obtain between the inlet and outlet, will also reduce. So one of our primary criteria is to reduce this energy loss to atmosphere. So what are the different ways by which you can reduce this energy loss to atmosphere? We'll know in the further slides. So basically the overall losses and the efficiency of the collector has to be estimated to determine the performance. So in general, both theoretical as well as experimental consideration. So the instantaneous efficiency of flat collectors vary between 30 to 60. So as I said, why this difference in range is because of the change in ambient conditions. So if your ambient conditions are good, so your efficiency will be more. If your ambient conditions are not that favorable, then the efficiency will be around 60%. So, and there is still a lot of scope for improving this efficiency to from 60 to 70 or 80%. So, by adopting appropriate enhancement techniques. So, this enhancement can be possible either by active or passive means. So, as I said, active means you can use a pump to force the water through the fluid circuit so that more amount of energy you can absorbed by the fluid. Okay, however, you need to provide some extra energy to run the pump, so which we will not get it free. That means you obviously again you have to depend on conventional grid to power your pump. Okay, so which may not be advisable. However, another way you can do it is you can install a solar PV panel, and from that power generated from solar PV panel, you can direct it to the motor, and you can run the motor. But how far it is effective, we have to study. So coming to this specific to passive augmentation techniques, so a few techniques are listed here. There are many, but a few techniques which we are working have listed here. So altering the physical properties of the working fluid. So basically the mode of heat transfer happening in the collector is convective heat transfer, that is MCP delta T. So that CP, whatever is there, so if you change the CP, so CP is nothing but the amount of energy you can gain by raising the temperature of fluid by 1 degree. So if you are able to raise the CP of water, so more amount of energy you can retain. So that you can take the help of nanoparticles. I think in the morning somebody asked whether nanoparticles can be used for enhancing the efficiency. Yes, definitely. So this is what I am going to cover in the further slides. Then, so how we can use the nanoparticles is by developing the nanofluids. Okay, so you can use different nanoparticles to develop different nanofluids. So you can use the fluids either in laminar or turbulent flow. So laminar corresponds to your natural convective heat transfer, and turbulent corresponds to your force circulation. So there is a there are a lot of drawbacks of using these nanoparticles in laminar conditions. Why? Because basically the density, viscosity, and all other properties will change. So because of which, so the in a laminar condition, so there may be a possibility that the rate of fluid flow can reduce. And there are a limited amount of studies done by people because of this challenge. So there is not much literature available in laminar condition. So myself as well as a few authors only have attempted this laminar flow conditions. So usage of these nanofluids in flat collector for laminar flow. So there is a lot of scope, and we can study different nanofluids and say which nanofluid is performing better in the laminar conditions. But it is not that easy. So there are many challenges involved. So if you are able to find out the appropriate method by which you can use these nanofluids in a laminar condition, so then definitely there is a scope for patenting. Then a combination of fluids as well as other passive techniques like putting tapes into the flow will also be a good idea wherein we can improve the heat transfer. So basically what happens if you put a tape means, so the flow circulation will change. Actually, if you take a plain pipe, so if you send fluid, it goes in a straight line. So whereas in this tape inserts, so based on the shape of the tape, so the fluid circulation will increase, and there is a possibility that the tube surface can provide enhanced heat transfer to the flowing fluid. So coming to the first part, that is parametric analysis of flat plate collector. So what we have done is we have studied what will be the influence of different operational parameters on the efficiency of the collector. So wait a minute, I will have some water. So basically the solar radiation passes through the glass cover at an inclination to the surface. So maybe at one particular location, if you change the inclination of the collector, so what will happen and what will be the influence of this inclination on the collector performance is studied. Then the amount of energy absorbed by the collector absorber plate, then the energy transferred to the flowing fluid, what will happen under thermosiphon and post convection modes. And usually the plate temperature is greater than ambient. So for different plate temperatures and for different ambient conditions, so how the performance will change. So there are already established equations. So we modified that equations slightly for our requirement. And yeah, so for different ambient conditions and wind conditions, so if the collector is exposed, so what will be its effect? Then what happens if the spacing is changed? So usually in conventional collectors, it will be around 2 inches from the absorber plate to glass cover. So if it is slightly changed, what happens, or whether that 2 inches is the optimal gap that is needed between the cover and glass has been studied. So some of the reasons for efficiency is the solar radiation is dilute and transient in nature. Basically, whatever the radiation that is falling on the collector, so it will be diffused over that particular area. So unlike a concentrated collector, so all the radiation is not concentrated to one particular place. So usually around the area of the collector, so the radiation will be distributed. So that's why the efficiency is less. And the maximum radiation that you can receive is about 1000 watt per meter. So, and an FEC is not subjected to optical concentration of radiation. So as I said, it is diffused. So the heat losses happen from the collector from the 3 sides as well as from the top. Okay, so the 3 sides, whatever we call it as bottom and side losses. And most of the energy loss is happening from the top. Why? Because we have changing dynamic changing operating parameters like wind speed and the ambient temperature. So for that changing conditions, so definitely the losses will be more. So in common, we can say, we can understand how the losses are happening from this figure. So whenever this 100% energy is incoming over that glass, so because of this glass properties, so 8% will be reflected. So I already told in the first few slides that so 1/3 of the energy that is received at the Earth atmosphere is reflected. So whatever is received on Earth, on that horizontal surface. From that also some 8% reflection is happening because of this glass surface. And since glass has some properties, so it will absorb some amount of heat. And then yeah, some 8% reflection will happen at the absorber also. And since there is air gap between this glass and absorber, so some convective losses happen, which is about 30%. And since this absorber will be at a high temperature and glass is at a low temperature, some radiation loss happens, which is about 6%. So these are all average numbers, not so because based on some specific operating parameters, these numbers may change. So whatever the numbers shown here are average. And absorber collects about 60% of the energy from the 100% what is incident on the collector. Some conductive losses happening, which is about 63%. So that's why I told. So the range of efficiency of the collector is in between 30 to 60%. So this is the amount of energy that is going to the fluid. Again, the fluid will go back to the storage tank, right? So at the storage tank also some losses will happen. So corresponding to all the losses, so you can say the efficiency of collector is somewhat reduced. Yeah, this is the different modes of heat transfer happening in the collector. Okay, so Q sun is the incident heat energy that is received on the collector, and some of the heat is emitted. Some of the heat is lost due to the wind flow. Then some loss is happening because of conduction. So like that. So different losses are there. So yeah, conductive, convective, and radiative losses happen because of various reasons. So conductive loss, though you provide proper insulation, you may not say that it is restricting 100% of the loss. So some convective losses happen because of the air presence between the glass and the absorber, and radiative losses happen from the absorber to the glass. So like that, different losses happen. So we need to find out appropriate ways by which you can reduce the heat loss. So basically, what our aim has to be is to transfer the heat that is absorbed by the absorber plate to the fluid. That means, so you need to maintain the absorber plate temperature as low as possible, so that you can get the heat transferred to the fluid. That means if you use this passive enhancement techniques, so it should result in lowering the plate temperature for the same condition. Okay, let us say you have kept one reference flat plate collector and another flat plate collector by including this enhanced techniques. So if you compare those two, so the absorber plate of the reference should be higher, and since you have incorporated passive enhancement techniques, so the absorber plate temperature will be somewhat lower than the reference temperature. Why? Because more amount of heat has been transferred to the fluid, so that's why the absorber plate temperature has been reduced. So that is our main objective. So we can understand this energy balance of flat plate collector. I think these formulas are already available in many textbooks. So Q useful is the amount of heat that is absorbed by the fluid. Okay, so useful heat that is delivered by the collector, and S is the amount of energy absorbed by the absorber plate because of the incident solar radiation. And as I said, as the area of absorber plate increases, so the more amount of heat can be absorbed. So your collector performance also indirectly depends on the area of the absorber. And QL is the heat losses that are occurring because of various modes of heat transfer like convection, radiation, and other things. So yeah, so at the denominator of this efficiency, you have the incident solar radiation, so which you can calculate using this formula. So the surface is not horizontal, so it is inclined. So you have so many other components coming into the picture. Yeah. So solar flux absorbed by this inclined surface is given by this formula. So we have this tau alpha coming into picture. So tau alpha is nothing but the transmittivity and the absorptivity of the current. So if you want to find out the instantaneous efficiency, that means at one particular instant, say you are keeping all the parameters constant, and if you want to find what is the instantaneous efficiency, so it is given by this formula QU by AP into TO. So where your area of the observer plate is constant, however your QU and the incident radiation will change according to the different operating parameters. So yeah, so coming to these heat losses that are happening because of various reasons. So you can use this appropriate equations to find out that. I'm not going into some more details. As I said, these are already available in the respective textbooks. So yeah, so what we have done, so we have considered so the main important influencing parameters that cause change in the practical performance. So the Parametric collector observer plate temperature has been varied from 310 to 390. So these values we got it from reference papers. So where people have experimented and identified that so the observer plate temperature can be in this range. And ambient temperature based on our local conditions, we have considered this. This is also average ambient temperature. And observer plate emissivity, we have changed it from 0.05 to 0.9. So why this change is there? So 0.05 means, so we have some proper selective coatings where the emissivity of the observer plate is reduced to 0.095. And 0.95 is the emissivity of a observer plate coated with normal black paint. Okay, so whatever the commercial paints that you get, if you paint it, so the emissivity will be 0.95. And if you have some selective observer coatings, so it will give you around 0.905. So usually all black bodies they absorb and emit more. Okay, so you need to appropriately change the properties of the paint such that the emissivity is reduced 0.05. And this emissivity has been prescribed by Bureau of Indian Standards also. And usually the glass cover emissivity will be 0.88 because of the material property. This we cannot change. And angle of inclination, we have changed it from 20 to 80. And the glass covers, we have ready for one as well as two glass covers. And wind loss also based on some experimental data, we have identified that the wind loss quotients can be in between 5 to 30. And since I said we have concentrated on laminar flow conditions, so we have taken the Reynolds number of flow to be in the range of 200 to 2000. So 2000 means less than 2300, so in the laminar condition. And spacing, we have changed it from 20 to 25. And heat flux in the range of 300 to 1200. So we have taken 1200 as the higher side. Since I told the instantaneous efficiency, so there may be some instances where the radiation can go beyond 1100 also in instantaneous. Yeah, these are the results. So before we have to do some validating things to validate our numerical code. So we developed one numerical code and validated with the experimental data available. So yeah, so we varied the emissivity of plate from 0.05 to 0.95. And when we put our experiment, so this experimental data also we performed by ourselves. And when we put our experimental data, so the emissivity is coming close to 0.1 to 0.05. So which implies that whatever the coating that has been provided to the collector is selective coating. So yeah, from this graph, you can see that so the more the emissivity of the observer, so the top loss coefficient will be more. So in the previous equations, I have shown that this U, top loss coefficient, is the major contributor for losses. So the more the emissivity of the plate, the losses will be more. So one of the criteria is that so your emissivity of the plate should be as low as possible. so that the top plus. So we cannot make it 0, but however, we can reduce it to a maximum extent. So whatever may be the plate temperature, so the losses will be reduced if your emissivity is low. Then we have also worked on what happens if the spacing as well as the wind loss solution change. So we can see that for 0.025, that is 25 mm gap, so the losses are reduced. So if you increase the spacing, so the losses are increasing, as well as so we can see that losses are lower for HW lower. Yeah, similarly for 20 degrees inclination and glass emissivity 0.88 and one number of glass cover. And for ambient temperature of 300, if glass temperature is varied, so what will happen to the loss coefficient? So you can see that if the glass temperature is lower, so the losses are less. So if the gas temperature is higher, so the losses are getting more from the top. So what the reason here is that if your glass temperature is more, so the wind will try to take away the heat from the glass. So that's why there will be more amount of radiation coming from the absorber to the glass. So if you are able to maintain lower glass temperature, so the possibility of losses are reduced. Similarly, for different plate temperature, so you can see that if your plate temperature is lower, so it is about 350, and we have taken the ambient temperature to be 303. So if the temperature difference between this ambient and plate is less, so the losses are less. But this condition we cannot attain anytime. So usually the temperature between ambient to plate will be more than 20 or 25 degrees always, because of the material property of the plate. Yeah, similarly, how does this efficiency vary for different glass temperature? So you can see that if your glass temperature is maintained higher, so the efficiency is lower, and if your glass temperature is maintained lower, so the efficiency is getting increased. So for different observer plate emissivity, so lower the emissivity of the observer, so higher will be your emissivity. Sorry, higher will be your efficiency. So similarly, we have also taken the different case of changing the plate emissivity. So lower the emissivity, so lower will be higher will be your efficiency for different plate temperatures. So like this, we have studied for different cases. So I think time is now 12:44. So that there are many things to discuss. May I know up to what time I can go for? Hello. So up to 1:10, can I continue? Hello.
Yes, sir, you can do.
Yeah. So maybe it might be something boring for you if I go on showing the same thing. So let me skip this. So coming to the actual thing, passive enhancement technique. So we have already seen that. So you have to reduce your plate temperature as low as possible, so that more amount of heat transfer takes place. So some of the techniques you can use is go for specialized absorber coatings, and include some flow turbulators inside the pipe, and change the working fluid properties. So for today, I am planning to concentrate only on this changing the working fluid properties. As I said, you can use nanofluids for as the working fluid. So one of the drawbacks of this use of nanofluids is that though you increase the heat transfer and rate and efficiency of the collector, but obviously have to go for a heat exchanger type storage tank, because we cannot use nanofluids for bathing, or you cannot use nanofluids for cleaning your utensils and other things. So definitely whatever the heat that has been gained by this nanofluid has to be transferred into the water that is there in the storage tank, and that storage tank water only you can use it for normal purposes. Okay, so the other requirement for using nanofluids as working fluid for rapid purposes is that you have to go for a heat exchanger type storage tank. Whereas in normal collector, so the water that you use so will be flowing over the collector. But since the properties of water are you can say that the heat transfer rate of water is lower than nanofluid. So the efficiency of the collector we can improve. So we can use different types of nanoparticles like Al2O, 3KO2, copper oxide, copper, and other particles for preparation. So you can use this, you can prepare these nanofluids by either a single or a step process. So I think I am losing time. Okay, I can just go through it. So these are the different, so this work has been conducted along with my collaborators in Malaysia. So actual experimentation happened in Malaysia itself. So they have prepared different SiO2 concentrations. And here, yeah, this is very important. So while preparing your nanofluids, you have to have a compromise between the thermal conductivity, density, and the specific heat. So if you go for copper, so it has a specific heat of 386, but its density is 8,954. However, if you come for SiO2, so its specific heat is 745. I think it's almost double, but its density is 4 times lower, that is 2,220. However, if you look at compare the thermal conductivity of copper is 383, whereas SiO2 is only 1.4. So here, what I want to stress is that so if you are if you want to prepare your nanofluid, so you can use a small amount of copper to get more heat transfer because the thermal conductivity is more. However, if you want to use SiO2, so the concentration of SiO2 has to be more, right? Because its thermal conductivity is lower, but its specific heat is higher. But that means it can store more amount of heat, but the heat transfer rate is lower, so you have to use more amount of SiO2. On the other hand, based on density, if you see, so your density reflects on the viscosity. Okay, so the more the density, so the viscosity will be more. So you need to have a compromise between all these three properties while choosing your nanofluid. Yeah, so you can estimate the properties by using these established relations. Yeah, as I said, along with the collaborators, we have finalized these parameters based on standard deviation and all. We have checked with other literature data, and we have finalized these equations. So these are called the regression equations. And you can see that thermal conductivity depends on the phi is the volume fraction. Volume fraction is the amount of nanoparticles you add to the fluid, and the temperature of the fluid, then the diameter of the particle, and the thermal diffusivity. So alpha P is the thermal diffusivity of the particle to the thermal diffusivity of water. And one thing you have to understand here is that so there are some exponents for each of these. So you can see that for the diameter of particle, the exponent is negative. That means, so if you increase the particle diameter, so there is a possibility that the thermal conductivity may reduce. So you need to go for lower particle diameter so that you can have enhanced thermal conductivity of the nanofluid. Similarly, on the phi, you have 1.37. That means, so this volume concentration is also highly dependent on K. That means, higher the concentration, so the higher will be the thermal conductivity. Yeah, similarly, density, specific heat are also mentioned. And coming to viscosity, so here also if the diameter of the particle is more, so there is a possibility that viscosity may increase. And the temperature, obviously, if the temperature is higher, the viscosity will be lower. Yeah, so some of the considerations that people have taken is nanofluids are Newtonian. in the low volume concentration, and thermal conductivity increases with concentration and temperature. Viscosity increases with concentration, and it will obviously decrease with temperature. Specific heat and density of nanofluid are determined based on law of mixtures. So I have some few questions so that you can understand it better. So I think I have shown some few equations, so we can just get answers for yourselves. So what are the nanofluid properties which are dependent on particle size? And maybe I will share this PPT later to the organizers, so they will give this PPT to you. So later you can find out the answers for these questions. And yeah, what is the effect of nanofluid under natural convection? As I said, so there are very few studies people have done on this enhancement of natural convection with nanofluids. So what people have identified is that so when the nanoparticle is added, so the heat transfer rate is decreasing in natural convection mode. So usually, if you add nanoparticles, so people have a wrong view that so the heat transfer will enhance. So this red line is for the simulated results, and this black line is for experimental values. So there is a gap between this experimental and simulation, why? Because in numerical simulation and all, we take some assumptions. So probably because of the assumptions not satisfying. So this variation is there. However, you have to understand here is that compared to water, so the nanoparticle, when you add nanoparticles to water under natural convection, it is getting reduced. So this is experimental setup that people have used to conduct the natural convection test. And also that people have, see here you can see this is the trend for experimental values. So it is from 20 to 30 for 1% volume concentration. For 4%, you can see that it is from it is further reduced. So the more the concentration you add in natural convection, so the Nusselt number or the heat transfer rate is decreasing. So the NU is decreasing with increasing particle concentration. So the reason that people have told is due to the slip between the nanoparticles and the fluid particles, which disrupt the suspension of nanoparticles inside the liquid, especially at very low velocity happening under natural convection flow. So similar test has been conducted by many researchers. So using not only with Al2O3, with multi-walled carbon nanotube based nanofluids also, and they observed that the same trend. So by increasing this concentration, so this is done on a real flat bed collector. So they have identified that the efficiency is increasing, but we cannot say compare this efficiency with the heat transfer rate when you are using this nanofluids. So they have done it for the CuO water also, and they have identified that the efficiency is increased with adding more nanoparticles, but not the heat transfer rates. So they have done for Al2O3 also, and they have done that. So, but there is a small variation between the change in efficiency, but definitely the efficiency of the collectors change. So, yeah, this is for turbulent heat transfer. So, yeah, sorry, not turbulent, natural convection only. So, one of our collaborator has done this work, and he made a test section, something like this, having a heating chamber on one side and cooling chamber on the other side. So this is the test section in which the fluid is sent under natural convection, and they have identified what will be the effect of this. So they have made a set of experiments and identified that so water is having higher Nusselt number compared to the nanoparticles. So here you can see these circles are the water, and triangles and star ones are for nanofluid. So they also observe the same thing. So for compared to water, so the heat transfer rates are reducing with adding nanoparticles to the base fluid under natural conditions. And the same trend for, is observed for TaO2 also. So coming to this forced convection, 10 minutes of it. So coming to this forced convection, so people have done for the L2O3 copper the same fluids what has been used for natural convection. So one important thing you have to understand here is that if the volume concentration is less than 4, then only the heat transfer rates are good. Okay, so more than 4, you should not prefer. So why I will tell you. So these are the equations. Okay. So yeah, you can see it from this. These are different things. So yeah, you can see it from this. So this is done for SiO2. So you can see that the property enhancement ratio. So if it is more than 4, so the heat transfer rates are getting decreased. So what is this property enhancement ratio? Is the ratio of enhancement in viscosity to thermal conductivity. So according to this magnitude, order of magnitude analysis, pressure and other authors have told that heat transfer enhancements are possible if the viscosity to thermal conductivity ratio is less than 4. So if it is more than 4, you should not prefer these nanofluids for enhanced heat transfer. So that is what you have to understand. So this has been summarized based on different experiments conducted by people. So yeah, sorry that it has skipped. Yeah, so this is for lower volume concentration of 0.05. Heat transfer rates, you can see the trend in change in heat transfer rates for SiO2 and TaO2 respectively. So that means TaO2 is giving better results compared to SiO2 for 0.05. So whether the same thing is for 1 or not, so we have tested. So here also TaO2 is giving better compared to SiO2, and for 2%, so you can see that yeah, so TaO2 is coming closer to water. So that means more than 2. So the TaO2 should not be preferred. Okay, so but SiO2 is giving you a better enhancement rate compared to TaO2 at 2%. So you should limit the volume concentration that you will add to the base fluid before going to the actual application. Similarly, for 3 also, whether it is only for 2 or not, we have tested, but for 3 also it is showing the same thing. That means TaO2 is having the same heat transfer rates as compared to water, but SiO2 at 3 also it is giving better enhancements. So if you want to prefer SiO2 and TaO2 for different concentrations, so you can use this data for the respective application. So generally for laminar conditions and all, you can use it in electronic cooling equipment. Yeah, coming to this enhancement ratio, you can see that so up to concentration 1, so the enhancement ratio is 1.24. So more than 1, so you can see that the enhancement ratios are getting reduced. Similarly for SiO2 up to 3, it is okay. So more than 3, so SiO2 is not preferred because the enhancement ratio is falling down. So yeah, and you can use this tester tapes along with nanofluids for enhanced heat transfer. So maybe I'll summarize this with a table because lack of time. I have more things to show, but yeah. So here you can see that yeah. So for 1% concentration or twisted ratio 5. So let me show you that twist ratio. Yeah. So H by D is the H is the distance between one twist, and d is the diameter of the tube. So since we are taking a cylindrical tube, we have diameter. If you have any other cross section, means you can calculate this hydraulic diameter, and the corresponding you can find the h/d ratios. And these are the different tapes that you can insert. So h/d ratio 93 means it is almost plane. So lower the h/d ratio, so higher will be the number of turns. Okay, so what will be the effect of these turns on heat transfer has been studied. I will show you that summary table so that you can easily understand. So this is for TaO2 with twisted tape. So for if you are having twist ratio of 5, so at concentration 1, you are getting highest thing. And similarly for twist ratio 10, so at 1% concentration, you are getting the highest enhancement ratios. So for others, it is lower. Similarly, 15 and 93. So 93 means almost a plain tape. So at 1% concentration only you are getting. So I think in the earlier slide I have shown that for TaO2 1% is the effective one. So for that 1% only you are getting the highest enhancement ratios. Similarly for SiO2 we have seen that 3% is good. So the same is shown in this table. For 3% only you are getting the highest enhancement ratio. That means in the actual application also, so the 3% SiO2 is giving you better enhancements. This is for 5. This is the enhancement ratio. So that means for lower twist you are getting better enhancements. So for 5 it is 98 and for 10 it is 68. So if you look at for 15 and 93 also, so it is somewhat reduced. So here it is 98, 68, and it is 57 and 52. So the more the twist ratio, so the enhancement ratio is reduced. So you have to go for lower twist ratios and up to 3% of SiO2 concentration, you are getting better results. So based on this, some generalized regression equations for heat transfer are done. I think you can go through some literature papers published to get the. Similarly, for friction factor also. So one of the drawbacks of using twisted tapes is that so the friction factor will increase, right? Because you are adding obstruction to the flow. So what happens to the friction factor is also studied, and correspondingly the regression equations for different nanofluid concentrations have been obtained. And for a different Prandtl number ratio, so Prandtl number 5 to 7. So this is for water. That is why Prandtl number ratio is 7. And we have another thing called hybrid nanofluids. So instead of using one nanoparticle, if you can go for multiple nanoparticles. So here you can see that the multi-wall carbon nanotube with ferric oxide and water. Okay, Fe3O4 means ferric oxide. So what you can do is you can take these two materials separately. You put it in a ball mill, and you have to use this some chemical called PVP. And if you do the ball milling for 2 hours, so then you will be getting this hybrid particle. And if you use in that application, what will be the enhancement rates are shown here. So if you go for only Fe3O4 water, so the enhancement is only 21% for 0.3, and the same is 31% for 0.3 volume concentration at the same temperature, 60 degrees. So you can get some 10% improvement if you go for hybrid nanofluids. And similarly, some other researchers have also studied what will be the enhancement ratios for different particles. And out of this, you can see that so this is 93.5. So actually, fly ash is a waste product in power plants. So that fly ash you can take and you combine with copper, so you'll be able to get 93.5% enhancement. Whereas the only fly ash water will give you only 67%. So all these combinations you can try based on your requirement and based on the application. So coming to the summary of all this work. So the parametric analysis has been undertaken, and the performance of this collector has been studied for different plate temperature, and from the analysis, the wind loss quotient as it increases from 0 to 10, so the glass temperature reduces from 57 to 37%, wherein you can reduce the different types of losses happening in the collector. And the absorber temperature is found to decrease with the increase of tilt angle. As I said, from 20 to 80 we have changed. So as the tilt angle of the collector increase, so the absorber plate has been found to decrease. So that means the intensity of radiation falling on the collector has reduced. So the glass temperature cover is observed to be decreased with increase in the wind heat transfer coefficient, as it is obvious that more the wind, so the more the heat loss from the ambient cover to ambient will takes place. And there is a limited analysis reported on natural convection heat transfer with nanofluids. So there is a lot of scope for young people to do some more analysis on this natural convection heat transfer with nanofluids. Both CFD and experimental investigations demonstrate that nanofluid as convection heat transfer will reduce the heat transfer rate with increase in the concentration of the nanofluid. So coming to the forced convection heat transfer, so the viscosity and thermal conductivity plays an important role in the heat transfer rates. So, and you should not go beyond a certain value of concentration of nanofluid, otherwise it goes waste. So there is no significant influence of particle size observed on heat transfer. So though there is a change in properties of the fluid, but if you come to the heat transfer rates, so the influence is found to be negligible. And under forced convection, the surface temperatures are observed to be lower when nanofluid is replaced with water. So some enhancement in heat transfer rates for forced convection, not for natural convection, has been observed. So the values of friction factor with nanofluids under forced convection are higher because of the change in their density and viscosity values. So which is about 5 to 15%. And forced convection with tissue tape enhance the average Nusselt numbers by 2 times for nanofluids compared to water having TIS ratio of 5. That means you should have lower TIS ratios so that enhancement in heat transfer is good. So I hope I have completed my presentation. So if you have any doubts. There are some few references also listed which you can. And I thank the organizers for giving me an opportunity to present.
Sir, we have a few questions in the chat box. So can you check it? What is the future scope of parabolic throw collector for research and PhD work?
Let me come from the first thing.
So the first question starts from what is the future scope of parabolic throw collector for the research and PhD work?
Yeah, definitely there is a lot of scope. As I said, if you can work on new materials. So actually one of the drawbacks of this parabolic throw collector is its mirror. Okay, so mirror, if you see, it is made of glass, so which is very brittle, and it cannot sustain for a long time. So one of the main drawbacks that people have identified is that the mirror replacement. So one thing is that it is very costly. Why? Because you have to use low iron glass mirrors. So these low iron glass mirrors are made of white sand. So this white sand is available only in a few countries, and not in all countries. So that's why only a few companies are manufacturing this low iron glass based mirrors. So if you have any appropriate material that you can identify which can replace mirror, so definitely that will be a novel one. And regarding this, heat transfer rates and all, you can use this nanoparticles as the in addition to the working fluid, so that the heat transfer rates are improved. So anyway, in your parabolic collector, the working fluid you take is heat transfer fluids, so having very high boiling point. So if you add these nanoparticles to this working fluids, so people have found out that the enhanced heat transfer rates are possible. So in that way, if you add nanoparticles, so there could be a chance that the volume of working fluid that you use may reduce. Next question. I hope I have answered the point.
The next question is, could you give some information about the standard sources, that is softwares, to collect the solar heat flux and the surface air temperature data?
Yeah, so actually one of the references that you can go for Indian conditions is IMD, International Meteorological Data, but it is not available free. However, some softwares which are released by NASA and NREL, so they provide the data based on GIS, that is Geographical Information Systems, which may not be accurate. The problem is with the accuracy of data and the period. I think they are giving you monthly data, not daily data. Daily data is available only with IMD, which you have to purchase. For some locations, they are available free. Probably if you can approach through suitable source, you may get it free also. Yeah, any other question, please?
Could you give some information about possibility to improve the efficiency by direct absorption solar collectors with nanofluids?
Okay, can you repeat it?
Possibility to improve the efficiency by direct absorption solar collectors with nanofluids.
DASC. People have also used that. As I said, when you go for nanofluids as a working fluid, definitely you have to have one heat exchanger component added to the system. So obviously you have to have an effective heat exchanger added to the device, so that the change in the efficiency, you can actually use it for the application. So actually when you add components to the system, so the overall efficiency will definitely reduce. So when you go for direct absorption collectors with nanofluids, so definitely you have to go for heat exchanger to be added to the system.
How can we avoid losses in the flat plate collector?
Yeah, that's what. We have to, if we can control the top loss coefficient, so definitely the collector performance you can improve. So one of the there are different ways. So some of the ways I have presented in my presentation, like changing the working fluid temperature, then improving the insulation characteristics, and you can increase the absorption rate of absorber collector by changing the material, or by including some new methods by which the absorptivity can be increased. So currently around 90% is the absorptivity rate. So if you are able to improve further, so the amount of heat that you can retain on the observer plate can improve. Yeah, economically justified to use nanofluid means, that is one of the major drawbacks. So currently, these nanoparticles are produced by only few companies like Sigma Aldrich and Alpha S. So if you are able to come up with some cost-effective chemical techniques by which you can produce these nanoparticles, so definitely the economics can be targeted. So how much electricity can be able to generate through FPC? So that's what I think this question has been answered by Professor Reddy sir also. So technically it is possible, but economically it is not feasible. So electricity generation, you can go for this organic Rankine cycle based systems. So where these organic Rankine cycle systems require low temperature of about 80 to 120. And since you use the low boiling point fluids in the organic Rankine cycle, so you can definitely evaporate this low boiling point fluid with 80 to 120 degrees temperature, and you can operate it. But you have to look into the economics also. So coming for the maximum electricity, so you can go for kilowatt scale application also. Modular systems are possible. But the problem with that is that in organic Rankine cycles, you need to have a expander. So manufacturing an expander to that capacity is very difficult. You have to go for a customized one, so which makes it more costly. If it is a regular available market available thing, means it is okay. But if you go for a specified configuration, means so the cost will increase. How we can contrast between PTC and FTC in terms of performance and economics aspects? Yeah, definitely the thermal efficiencies are more for parabolic trough collectors. Why? Because you are concentrating energy to one point. Whereas in flat plate collector, the same amount of energy, it is falling on a diffused space. So that means the energy is becoming diffused over a certain area. So actually, if you look into this parabolic trough collectors, there are two concentration ratios, that is geometric concentration and optical concentration ratio. So where this geometrical and optical concentration ratios are more for parabolic trough collectors, and it is quite less for flat plate collectors. So that's why the efficiencies are getting lower. And coming to the economic aspects, so PTCs are generally used for high temperature applications. So generally you can go for about 400 degrees or so. Whereas these flat plate collectors, you can get a maximum of about 70 degrees. Okay, in normal flat plate collector. If you go for ETCs, you can get up to 120 degrees also. I think I have answered. Parabolic trough collectors are somewhat costly compared to flat plate collectors. So, and parabolic trough collectors, you cannot build it on modular scale. Okay, so whereas flat plate collectors, you can go for a modular scale. Parabolic trough collectors are somewhat costly, as I said. Mirrors and other things are involved. So actually, the maintenance and other aspects are more in parabolic trough collectors compared to flat plate. Is there any other questions from the audience?
I think questions session are over.
Yeah, you are. One more thing to the audience is that you are free to ask questions, maybe through offline, through mails or something. I'm happy to answer. I hope the session was interesting.
Thank you, sir. Thank you very much for your valuable. Just now we were listening to Dr. Y. Sekhar, Associate Professor, Department of Thermal and Energy Engineering, School of Mechanical Engineering, on the topic Solar Thermal Collectors, Performance Enhancement with Passive Techniques. Through his presentation, we have gained many methods or ideas by which the efficiencies of thermal collectors, solar thermal collectors, can be improved. And many researchers got a breakthrough idea for their research work in this field as well from your presentation, sir.
Yeah.
In that way, all the participants were benefited from this session. I once again thank you, sir, for sharing your valuable time and knowledge with us. And we hope to see you again in the future events. Thank you, sir.
Yeah, thank you very much. Thanks the organizers for giving me an opportunity to present my work. Thank you.
Okay, thank you. Dear participants, the next session will